The key as we look at problems in thermodynamics is to pay attention to units, to pay attention to signs, and to keep really clear to ourselves what is the system and what is the surroundings, or at least to keep the different chemicals or the different parts of our systems separate. With calorimetry, we're focusing on heat lost and heat gained. So as we read our first problem and we have a piece of metal at a certain temperature and water at another temperature, and specifically looking at those temperatures, recognizing that they're fairly close to one another and not outside the boiling or freezing point of water, we can realize that one's just going to cool down and the other will heat up till they get to thermal equilibrium. And that means that we are going to end at the same temperature. This one says thermal equilibrium and says the final temperature of both objects. Sometimes this same question could be worded, what is the final temperature of the aluminum? What is the final temperature of the water? Without the obvious indication that they're going to end up the same. But in order to solve for this, we would have to be given our specific heat values, and we would need to know that the mass times specific heat times delta T for each is the same. Then we just have a little bit of work with algebra here. So if we have this set up all right, we multiply, we remember we've got a negative sign on one side. It doesn't matter which side, as long as we remember that it needs to be there. More often than not, I'll put it on the side that is decreasing in temperature just for my own clarity, but it does not need to be that side. It's just showing that they're opposite of one another. So to do this, it might be 1, 2, or 3 math steps that you go through. Or if you have a graphing calculator, it is possible to solve an equation like this using an equation solver where you don't need to go through all the steps and it will give you the right answer. That's totally fine. If we set it up, plug in the numbers, and then jump to the answer with the correct equations, we can still get full points on this. So the one thing that makes sense with this is that we're also ending between those two temperatures. Water has a specific heat that's 4 to 5 times higher than aluminum. So it does not change as much in temperature. There's 3 times as much water as there is aluminum, so it does not change as much in temperature. So that accounts for the fact that even though maybe something at 30 degrees would be right in between, we're going to be way closer to the water. So we should not only be able to do the exact calculations, but also make those predictions and explanations. The second one here talks about something that's in a bomb calorimeter and gives us the heat capacity, which is different than specific heat. Heat capacity accounts for the heat change per degree Celsius. So it doesn't matter how much stuff is there because the calorimeter already has a defined capacity, whether there's a lot or a little in there. So we just multiply our heat capacity times our temperature change, and that gives us an amount of heat. So we think about that. The temperature rose by less than 4 degrees. We've got that, but a whole bunch of kilojoules here. When it asks kilojoules per mole, we would then need to take the grams of our chemical, the sucrose. We've got that right there, a molar mass right there. We divide. It's very few moles. When I divide my kilojoules by my moles, which is how I get kilojoules per mole, it gives me a delta H. We'll define that soon, but that is called the enthalpy or the heat of reaction. And I have a negative sign here, which is important to show that it is released. Based upon the wording of the equation, you might not need the word or the negative sign because it says released, but it is important to recognize that we are releasing, or we now have less heat than we did before. And we'll come back and clarify that several times with problems and with notes. On part C, we're looking at another metal in water. We have a certain mass. We're cooling it from a temperature by placing it in water. We have an amount of energy. So we're looking at a change in temperature again. One thing that's key here is that energy is transferred to the water. That is energy lost by the metal. So that's why that 30,000 has a negative on it. We've got a mass, a specific heat, and then instead of just leaving it as delta T, I think about final temperature minus initial. The final temperature, if it's cooling down, has to be lower. That's our clue if we had forgotten a negative sign here or put things in the wrong order here that we've done it wrong. We can always kind of double check, do things make sense by looking at the magnitude of our numbers, but much more so whether they're increasing or decreasing. Excuse me. And then a few conceptual ones to connect here. When we drop a hot rock in a pail of water, the rock change until they're equal. The rock cools down, the water warms up, and we can probably measure both of those temperature changes. And if we're asked, does the same thing hold true into a large lake? The answer is yes. It's the first law of thermodynamics. It's the law of conservation of energy. Yes, but we would almost not even measure a temperature change on the pond. And that pond would also probably be losing temperature to the air and to the mud, the dirt, the sand around it. So the same principle applies, although it's much harder to measure it for the pond, but the rock, definitely an easy temperature change to measure. And then the last thing here does apply to our definition of thermal equilibrium, of average kinetic energy, and of temperature. If we have a block of ice and we have a gas-filled balloon, both at 0 degrees, they both have the same average kinetic energy of the particles. That doesn't mean that they're moving at exactly the same speed, because they might have different mass for their particles, but the same average kinetic energy means the same temperature. So if I put my balloon near the ice, my ice inside the balloon, there would be no transfer of heat back and forth. That makes sense in that scenario. But one thing that's sometimes a little bit trickier is that we can have ice at 0 and liquid water at 0. And as we start to look at changes in state and changes in phase, it is important to remember what's happening there. Heat only flows when there is a difference in temperature. So because there's no difference in temperature, there's no difference in average kinetic energy, and no difference in average kinetic energy means no flow of heat from one object to the other.